Well, hi everyone, and welcome to our student revision tutorial on applications of differentiation. So as per the description, we'll be looking at a range of applications of differentiation and really focusing on what students can use in their exam, of course, or in their technology active assessment tasks throughout the year. So my name's Hayley. I am a teacher and I currently teach Year 11 and Year 12 maths methods. And it's a pleasure to be hosting this webinar for you today. So in the session, I'll be taking you through some example questions. The questions I've picked are the sort of questions that you might get on an exam, either multiple choice or extended response. And I'll hopefully be able to show you some frequently used commands, maybe some shortcuts and some tips and some tricks. So we're going to start off with this example here. It's just a function here that's the product of two functions, and we're asked to find the derivative g dash of x, and this is a multiple choice question. So of course during the year you will learn, or will have already learnt, the chain rule and the product rule, so you'll be able to differentiate this by hand. But if you were in a situation where you had your calculator, we can use our CAS to do this. So I'm just going to go into my math box here and change this to an assign command and press enter. Now, the document that I'm working in, I'm using a notes page. So when you insert a new page on your in your CAS, Control-I is the shortcut for a new page. And you can choose the ones we probably use most often, of course, the calculator and graphs. But this notes page here is really handy. This allows you to type text, and it also allows you to insert what's called a math box, as in M-A-T-H, math box. So in a notes page, you can type text, so something like calculus. I know it's a little bit annoying, but your keypad is not QWERTY. However, on a computer, you can type quite easily if you have the software. And then you can insert a math box, and inside that math box, you can define a function using Control and this button here next to 9, and that will help you to define a function. And I'll come back to these math boxes with other examples and show you why they can be incredibly useful. So if we've defined our function g of x, then remembering that these pages talk to one another, if I open up a new calculator page, my function g of x is defined here. So the shortcut for to find a derivative function is shift and minus. That will bring up my derivative template. Now, if you didn't know the shortcut, then you'd be going through menu and then calculus and then, menu and then calculus and number 1. So menu for 1 would be the shortcut. This shift minus shortcut is quite useful as well. So of course we're differentiating with respect to x, and I could type in that function here, x squared multiplied by positive 2x, but I have defined my function, so I just type in g of x, and I will get my derivative function there, which of course was one of the options in our multiple choice list. So of course you need to be able to do this by hand by the end of the year, absolutely. However, if it was on a multiple choice question, it sort of makes sense to at least double check your answer using the calculator function there. So we can also use this template to find the derivative at a specific point. So had the question said, find g dash of 2, for example, instead of asking us to find the derivative function, they want us to find the derivative when x is equal to 2, then we can do that. Now, I could retype this in, or I can use another handy little shortcut, which is that if I just use my keypad and press up until I've highlighted that text there, and then I press enter, that will drop the text back down into a new line. Rather than doing copy and paste, you can copy and paste on a handheld. Control-C and Control-V work. However, it's a little bit clunky to highlight something on a handheld. So That's a nice shortcut. I just clicked up until it was highlighted and then I pressed enter. And of course, we can put a little given that symbol on the end here and say given that x equals 2, and that will find the derivative of our function when x is equal to 2. And then, of course, you might want that as a decimal, so you can press Control Enter to get a decimal approximation. Okay, so nice little syntax hints here. That is the same template that would come up if you had gone through menu, calculus, and derivative at a point, and then typed in your variable here. That template would come up, of course. We can type that in manually. I think it's quicker to type it in manually. Okay, so let's have a look at another question. These are just common sorts of questions that you might get on particularly exam 2. This question is saying if y equals the square root of x plus 2x squared, then the rate of change of y with respect to x at x equals 1 is. Okay, so this is a great example of where they're asking us to find the derivative of a function at that particular point. Now, I've used a math box here, so I'm going to come in and define my function. I'll just use f of x and use the assign command. Okay, if I do that, then my function is automatically defined in another page. And so, let's come over here. Control I will be the shortcut to open a new page. And here I can use that same method, so derivative at a point. So shift minus, and I defined it as f of x, given that x equals 1 is the question. And that will give me my solution straight away, that the derivative of the function when x is equal to 1 is 5 root 3 on 6, which is, this is a great question because our solution, our CAS has actually rationalised our denominator. So then we would need to work out from this list of options here, which of those values is going to be the right one. And we can probably do that fairly easily. You'd be looking at something with an irrational denominator. So to get 5 root 3 on 6, we're going to be rationalising 5 root 3 on 6. It'll be e by the looks of it. I think someone can yell at me if I've done that wrong. That looks about right. And you could, of course, check. If you weren't confident with that, you can convert your answer into a decimal and then compare from the multiple choice responses in that list. Great question. Okay, now I'm seeing a little question pop up, and I'm glad you asked that, Elaine. So I want to talk about what I'm doing here with my different tabs open. You may have noticed that I've got 1.7 and then I jumped to 2.1. And in fact, if I just scroll across a bit, I've got all these different problems. So problem 3, 4, 5, etc. Now, this is really, really useful for students, particularly in exam 2 or even in stacks where you have sort of multiple choice. You might have a couple of questions and a separate extended response question. So I'm going to explain what I'm doing there. When I want to insert a new page, my shortcut was Control I. We've seen me do that a couple of times. And if I insert a new page here, Control I will insert a page just in this same problem. So 2.3, I could add another page, 2.4, etc. If you want to add a new problem, you go to the dock key, which is above menu, and number 4 is insert, and number 1 is problem. So it's dock 4.1, dock 4.1. Now, the benefit of adding a new problem, and this, of course, will start problem number 3, it bumps problem 3 to problem 4 and so on. The benefit of this, there's a few great benefits. Now, let's jump back into problem 1, where I had defined a function f of x. If I hit my var key above number 9, you'll see that I have my two functions here, f and g. They're the functions I've defined in problem number 1. But if I jump into problem number 2 and hit the var key, you'll see I only have f because I've only defined f in problem number 2. So this means you can reuse a function name. You can store f of x as one function in problem 1 and then as a completely different function in problem 2. And particularly if you're using the same label like f of x, it will save you some confusion here. So if we jump into problem 3 and hit the var key, nothing is defined x in problem number 3. Now you can delete the page if you accidentally insert one. So you go to page layout and you can delete your page. So that is doc 5 and 6 is the shortcut there. We can get rid of that page. That's a really useful thing because sometimes you add one in there by mistake. And to see an overview of everything, you press Control and up. And now you can see all your problems. This is great. So you can scroll from one problem to the next. You can use the up key on your handheld, and that will take you from one problem to the next problem. It's really quite cool. Well, I think it is. Okay, so let's go back here. We've just done problem 2. Control and across will get you to the next page on a handheld as well. Let's look at this question. It's asking us for the average rate of change of the function d of x, where g of x is the square root of tan x, between x equals 0 and x equals pi on 4. Now, this question is not asking us for the derivative at a point. Okay, this question is asking us for the average rate of change, which is the gradient of a line or the chord between these 2 points. So if we didn't have technology, we would need to evaluate tan of 0 and take the square root of that, and then evaluate tan of pi on 4 and take the square root of that. Now, if you've done a little bit of trig recently, those values are actually not too hard to deal with. However, if we have a calculator, it's really useful to know how to do it. So I'm just going to jump in here in my math box and assign g of x as that function there. Now, something you may not have seen before is you can split your page. So if I want to do some calculations here in a normal calculator page, because this is probably what students would be using, you can hit the dock key and then go page layout, and you can select a layout here. I generally kind of use this one, okay? So I just split my page. That was through doc, page layout, and I'm going to make that a normal calculator page. Okay, so what I have here is my notes page sitting up the top with the question in it and a normal calculator page. So how do we find the average rate of change? Well, hopefully you remember that as being the gradient of the line between the 2 points, so y2 minus y1 over x2 minus x1. I can see a question. The documents page is just here. All right, so what we can do is say we have g of pi on 4. I can use pi on a handheld, or I can use the pi button, which is down next to the letter h. G of pi on 4 minus g of 0 over pi on 4 minus 0. So obviously you probably don't need to worry about typing that in. I'm showing you the long way, I guess, if we didn't know that there's a shortcut for this. So hopefully I haven't done something wrong. Hopefully that's one of my answers in there. It looks like it is. Beautiful. Now, there is a shortcut. So hopefully everyone's clear on this, y2 minus y1 over x2 minus x1. In your catalogue, which is the little book button here next to the number 9, if you click on that catalogue button, you want to be in the first tab here. So if you click the book button and then it opens up as one of these tabs, you just want to jump into the list here. And we actually want the command, I'll scroll to it. It would be quicker to click B, the letter B, and scroll up. Certainly would have been quicker. So you can hit the letter B on your keypad and then scroll up. And what we can see here is the average rate of change. And what we can see underneath there is the syntax. So when we're using the average rate of change command, we need to type in the expression. So that would be the square root of tan x, the variable, so the starting point, which will be, in our case, x equals 0, and then the step size, which in this case is going to be pi on 4. But I'll just clear that up. It's not actually pi on 4 because the second x value is pi on 4. It's pi on 4 because the distance between the 2 points is horizontally is pi on 4. So let's have a look. We type in g of x, comma, x equals 0 as our starting point, and then pi on 4, which is our step size. And that will give us the answer that we saw when we essentially did it manually. This is the step size here. So if we were asked to find the average rate of change, let me do an example here. If we were asked to find the average rate of change for the function, let's type in f of x equals x squared, between x equals 2 and x equals 10, then we would use the command average rate of change. Remember, that's on the book button there, and we type in our function. Sorry, I didn't press enter. Sorry. Type in our function f of x, our starting point, which is 2, and our step size would be 8 here. Okay, so it's the difference between x2 and x1, if you like, is the syntax. That's important because chances are the examiners will know that you might accidentally type in 10 here, and they'll put the incorrect answer as an option in your multiple choice list. Okay, let's have a look at stationary points. This is a pretty common kind of question where they're asking you either about the nature of the stationary points or the number of stationary points. What I might do is have a look at the graph. I know we don't need the graph in order to find the number of stationary points, but it's always useful to have a look at the graph. So it's going to define that function. And I can press Control-I and insert a graph page. And because my function is already defined, I don't need to retype it. So that is my, my function there. Thank you very much for that missed X there. So I'd like to say I'd done that on purpose, but I hadn't, just missed a multiplication sign in there. So thank you very much, Stephen, for picking me up on that. Okay, so let's try this again. We'll sketch f of x, and there's my graph. Beautiful. Now, it's not exactly the scale's not amazing. That's looking very narrow there. So I can fiddle with my scale just by double clicking on one of these values and changing that, and then pressing tab. So tab is just above control, and tab will take me to the next value on that axis. So I might want 50, something like that. I can reduce that value a bit and fiddle around with my scale until I'm sort of happy with the way that my scale is looking. So it's always a good idea to see the graph. Obviously, we're not seeing the maximum up there. Sorry, I'm going to, there we go. It's not a bad idea to have a look at it. But in terms of finding the number of stationary points, we don't need to use the graph to count them. We can do this in a few different ways. So what we can do is, given that we've already defined our function as f of x, we could, obviously the stationary points have a derivative of 0, so we could use the solve function to solve where our derivative is equal to 0. I'll show you how to do that. So you might want to do your derivative separately if you want. There's our derivative function. We can solve menu 3(1) is our shortcut. Solve where our derivative is equal to 0 for x. And what we're getting here is our stationary points as exact values, which of course, if we press Control-Enter, we can see as decimals. Now, this is a great example of why we could possibly use the zeros command instead of the solve function. So what we can see here is a list. I'm fully aware that on a handheld, this can be quite clunky, getting from this value here, going across. So Control-1 and Control-7 are handy little shortcuts to get you to the end of a long list. And that's really handy, particularly for trig when you're doing circular functions and you get a long list. However, you can get these solutions coming up in a beautiful set if you use the zeros command instead of using the solve function. So Zeros will find the roots. Essentially, it'll give you your solutions when the expression is equal to 0. So we can find where our derivative, shift minus, of f of x is equal to 0. We don't need an equals to 0 here. Okay? The syntax is that if it is equal to 0, so you just put in your expression and then comma x. And there are our beautiful solutions sitting in a set there, rather than having that big long list that we saw before that was a little bit clunky. So here we can clearly see, you could then count how many solutions there are. You can also use the count function, which you can, in this case, you can clearly see 1, 2, 3, 4, 5. It's not that hard to count them, but if you had 20 solutions or something like this, the count function is really useful. So we can access count in this list here, or we can count, type it in. And if you highlight that set and press enter, it will count the values. And that's something I'll show again tomorrow in the webinar about circular function equations, because often they'll ask for the number of solutions to an equation rather than the actual solutions. So hopefully that is handy. Now I might just show you at this point, for example, this is something you might really want to have in your bound reference as an example of the syntax, and you might want to just annotate the syntax, with a highlighter and remind yourself what you need to type in. So if you have the computer software on your computer, on your device, Control J is a shortcut. Control J will then take a screenshot of your screen. Sorry, Bella is asking where the count function is. It's in the catalog, honey. So in here, and you can scroll down to count, or D and scroll up, and you should be able to find it there. Sorry, so what I was saying, you can take a screenshot of any page, and that is hugely useful. Control J was the shortcut, and then it just opens as an image here, and you can paste that into a Word document, into a Google Doc. You can paste it into a PowerPoint if you really wanted to. It's a very useful command for students making their bound reference. Okay, so let's jump into question 5. We're asked about the minimum value of a function. So this is a really common skill or common question that you'll get asked, is about the maximum function of the minimum of a function. And you don't want to assume that the max or the min is at a stationary point. You actually do want to probably see your graph and double check that it's not at an end point. So I'm going to assign my function, and you could do this in a normal calculator page. I'm just saving myself some time here. So I've got the function g of x. I did use g of x in a previous question, but g of x is not defined here. It hadn't been defined until I defined it just then, as I'm working in a different problem. And I could put a domain restriction on the end here as well when I define my function. So I could actually is greater than or equal to, there we go, sorry, less than or equal to, and define my function there. Or you could just define it when you were in your so that's my function defined. I might have a look at my graph, so Control I, and then have a look at g of x, or I could have split my page if I wanted to. Just going to change my scale again. Go, right, and I did that by double clicking rather than going through the window, because if you go through the window, you're sort of looking at these numbers without being able to see your graph at the same time. I think it's nice to be able to just see your graph as you change the values. Now, what we can see here is that our minimum, be sure it asked us for the minimum is actually at an endpoint here. So if you had just assumed that the max or the min of a function was at a stationary point, then obviously, well, in this case, you would have the question wrong. But we can clearly see by looking at the graph that it has a local minimum over here. However, our actual minimum is down. So there's a few ways we can get that value. One way is that we can just work in a normal calculator page, and I'll split my page here so we can see normal calculator page. Here we go. And knowing that that endpoint is at -3, I could evaluate -3. Okay, and there's my minimum function value. If you want to use the graph, you can use menu, trace, and then trace graph, and you can type in -3, I press enter, and it will actually label that point on the graph. So that's another way to do it. There is another way to do it. So another way we can do it is to use the fmin or fmax function. In this case, it would be function minimum, which is this function here. So menu for 7, and then g of x comma x is our syntax. Now that won't tell you the minimum value. That's really important. This hasn't told us the minimum value of the function. It's told us the x value where the function is a minimum. Okay. Now, if they had asked us about the stationary points here, remembering that we can use the zeros command, which I've just typed in, but you can access that through menu algebra zeros. And the shortcut here, and I can differentiate my function and find where my function has a derivative of 0. Sorry, I pressed 0 instead of x. There we go. And what we can see is that we have stationary points at -1 and 2. And to find the coordinates of those points, you can actually just do G bracket and sub in the set. Oh, it's not liking that at all. Not liking that. G of -1 and 2. Sorry, do them separately. There we go. Beautiful. G of -1 and G of 2 separately, and we can find our coordinates. So using your graph in conjunction with a calculator page, not necessarily split like I have, you can have them in separate pages, is just really, it's smart to look at the graph as well as use the calculator page function. Okay, we only have about a minute left, or 2 minutes. I want to show you something really quickly. Equations of tangents and normals is something that we get asked about often. And so if you're asked to find the equation of a tangent or of a normal, which as I said is very common, you can define your function or not define your function. I'm going to define my function here to save me some time. And in a calculator page, you can hit menu and then calculus, and these two options here, tangent line and normal line. So make sure you read the question carefully and work out which one you want. Tangent line, and my tangent was on f of x at the point where x is 0. So I type in f of x comma x equals 0, and I will get the equation. And in fact, if I had typed in y equals before I used my tangent line, then it even gives you the equation in y equals 2x plus 2 form. As I said, you could have used the normal line. If the question said find the equation of the normal to the curve, let's imagine it's wanted normal at x equals 0. Obviously, we're expecting a gradient of -1/2 here, given that the gradient of the tangent is +2. And again, we could have put y equals there, and that would give us the equation there. So I am right on time. And I might stop there, but if you've got any questions, I'll stay online. You can feel free to ask in the chat. And thanks very much to everyone for registering today. Good luck with your study over the Easter holiday break, and tune in for the rest of the webinar series.